Perhaps the most pivotal time in the history of scientific advancement was the discovery of galaxies. For all of history, we have been able to look into the night sky and marvel at the band of the Milky Way, creating a cloudy stripe of stars in the darkness. However, it was not until the early 20th century when telescopes became sufficiently powerful so as to make sense of the systems known as nebulae. It was at this time when we first became aware that our galaxy was but one in a sea of many such systems. Through the discovery of means to determine their distances away, we realized the vast expanse of space between our own Milky Way and these nebulae. By recognizing their separation from our galaxy, we were introduced to an entirely new layer in the depth of reality. From this, what were called nebulae became known as galaxies. The critical piece of evidence used to calculate the distance of these nebulae was the presence of what are known as Cepheid variable stars. These systems pulsate at a regular rate, which has been found to be closely correlated with their luminosity, the amount of radiation that they emit. As a result, their distance away can be calculated by using their pulse rate and by how bright they appear to us, their observed brightness. This was a crucial moment in the development of modern scientific theories. Edwin Hubble used these Cepheid stars to show that our neighboring Andromeda galaxy was a separate and distinct system from the Milky Way galaxy. He also stumbled upon a realization that would change the course of science for the next century. When he analyzed the light spectrum coming from these galaxies, he found that they were almost always redshifted. What this means is that the light passes through particles which absorb portions of the light at specific wavelengths dependent on what the particles are composed of. We do the same experimentally in the lab to determine which materials produce which absorption patterns. When we look at the light from these galaxies, we see these absorption patterns exist, but at lower energy, shifted towards the red spectrum. This is known as a redshift. Hubble then proceeded to measure the distance of the galaxies from Earth using these Cepheid stars and plotting their distance versus the amount of redshift for each galaxy, and found a startling discovery. The two measures are correlated. What this meant was that the distance of galaxies from Earth could be accurately approximated by simply measuring their redshift. It did not matter which direction in space we looked, they all followed the same trend line. The question then was why? As we see here, Edwin Hubble concluded that this redshift was associated with the physical motion of the galaxies. In short, the conclusion was that galaxies moved away from Earth and that their velocity was dependent upon their distance away. Notably, redshift and velocity are not the same thing. Rather, a known cause of redshift is motion away, in this case also known as recessional velocity. The interpretation that this redshift is the result of motion is itself an extrapolation. In what is known as Doppler shift, when an object is moving relative to its surroundings, then the wavelength of emissions in the direction of the motion is shortened, while the wavelength in the opposite direction of the motion is increased. This is the case for all forms of waves, whether they be sound waves or light waves, coming from an object in motion. The shortening of the wavelength is known as blue shift, while an increase in the wavelength is known as redshift. It was concluded that the redshift of the galaxies we see was caused, therefore, by motion away. Thus, from the infancy of this observation, we began to take the subtly added step of translating redshift into recessional velocity. The reason this step is so vital is because redshift can also be caused by gravity in what is known as gravitational redshift. When light moves away from a source of gravity, it will be stretched into a redshift. Alternatively, if light moves towards the source of gravity, then it will be compressed into a blue shift. As these two forms of redshift can occur, it demonstrates that it is an assumption to conclude that the redshifts we see are even caused by motion at all. The question becomes, are the observations caused by Doppler shift or gravitational redshift? As we see here, it has become standard practice to translate redshift into recessional velocity. Moreover, it has become clear that a trend line of increasing redshift versus increasing distance exists. If we, for the time being, assume that motion is the cause of this redshift, then the first issue we run into is that as distance increases, so too does the recessional velocity increase. How high then does it go? Over much greater distances, the measured redshift begins to very non-trivially increase to a level where the underlying framework of our models of the universe became unstable. For example, here we have galaxy GNZ11. For Doppler shift, a recessional velocity of 0 has a redshift value z of 0. A recessional velocity of the speed of light, c, has a redshift value of 1. This runs into the issue that when z is greater than 1, the calculated recessional velocity exceeds the speed of light. In GNZ11's case, it does not just slightly surpass 1, but rather it is named this specifically because its redshift value is 11. If we keep walking along this path, the trail begins to get stranger. Nowadays, we say that the universe began in a Big Bang, and that essentially everything is spreading apart from everything else due to what is called expansion of space. We have yet to touch on this topic, though it is the next step we took in the path we are retracing. Beyond that came another foothold on the increasingly precarious path, this one known as dark energy, said to cause the rate of this expansion of space to accelerate. So how did we get here from the discovery of galaxies? What occurred next is subtle but telling. Initially, the journey began by extrapolation that the redshift was caused by motion due to Doppler shift. Once motion was associated with redshift, it became closely attached to the observation. Then, when these motions were seen to exceed the speed of light, it was concluded that there was more to what was happening. In order to prevent these galaxies from traveling faster than the speed of light in the model, scientists looked to the correlation of redshift per distance, which had become known as Hubble's law, and gave it a new specific name, cosmological redshift. Lastly, it was concluded that this particular section of the motion was caused by something yet unknown to science, expansion of space. As a result of this process, galaxies no longer were traveling faster than the speed of light, but rather, space was expanding. This is analogous to a sinking ship where a hole in the hull of the ship, the portion that keeps it afloat, exists. To prevent the ship from sinking, it is necessary to patch the hole sufficiently. Later, another hole was seen that needed patching, and this was done so by the inclusion of the concept of dark energy. And so, to summarize, when we interpret that the observed redshifts of these galaxies are caused by Doppler effect, this leads us to the inclusion of cosmological redshift, which we say to be the result of expansion of space, which leads us further to the concept of accelerating expansion of space when we more recently observed the rate of redshift per distance increases at very large distances and needed to explain the nonlinearity, which then leads us to inserting dark energy as the cause of this accelerating expansion. In other words, meaning the interpretation that motion is the cause of redshift leads to many new claimed underlying mechanics of the universe. Well, what about gravitational redshift? When we look at a distant galaxy, we see absorption lines that tell us the amount of redshift of the light. What we don't see is a tag on the redshift labeling what exactly is causing it. It is up to us to reason out why the redshift exists. It could very well be that the redshift is not the result of motion at all, but rather is the result of gravitational redshift. So it is important to consider this possibility when the interpretation of motion necessitates the addition of both expansion of space and dark energy. Added complexities are illogical and do not follow the ultimate progression of science, which always moves towards a more narrow and exact underlying description rather than expanding into many new root causes which add complexities. If this approach were reasonable, then at its extreme, every single aspect of the universe would have its own underlying fundamental laws, which would make nothing universal. Clearly, scientific progress is towards narrowed exactness, as is supported by logic and reason, such as in Occam's razor, where the simplest answer is the most likely to be true. So is it possible that gravity could cause the observations? This is the celestial sphere, which is a map coordinate system that indicates the position in the sky where we make an observation. With redshift, we see that 1. All distant galaxies are redshifted. In other words, this redshift occurs in all directions independent of the direction in the celestial sphere. This also means that it does not apply locally within what we call the local group. Secondly, the redshift of each galaxy is generally correlated with its distance away from Earth. This correlation has become known as Hubble's law, which we have labeled as specifically cosmological redshift. It is important to note that outliers do exist. In other words, there are exceptions, but generally speaking, the trend exists across the vast majority of observed galaxies. But what does it mean that this redshift does not occur locally? In the local group, we see many blue-shifted galaxies. As shown here by Courteau et al., each arrow represents a galaxy, and its color represents whether its light is redshifted or blue-shifted. At the center is the Milky Way galaxy, and as we see here, there are not only blue-shifted galaxies, but a noticeable dichotomy where half of the galaxies are generally redshifted, while the other half is generally blue-shifted. It is worth noting that some of the strongest gravitational anomalies known exist in the direction of the redshift, the great attractor in the Centaurus cluster, as well as the Shapley supercluster. It is because of these nearer galaxies that we add the particular detail that all distant galaxies are redshifted. According to the Big Bang interpretation, the existence of these blue-shifted galaxies is because gravity is more influential than expansion of space on this smaller scale. With this all in mind, we can ask once more, can gravity cause these observations? Before we attempt to answer whether it can, we can consider the potential benefits of a gravity-based interpretation. First, there is no need for adding expansion of space and dark energy to the model. From a logical standpoint, the simplest explanation is the most likely to be true. Added complexities are therefore unsound. Secondly, it could provide a pathway to making sense of the mysteries of the cosmos. Many observations remain unexplained within the current models, and perhaps because of the current models. Then there are the difficulties of a gravity-based interpretation, not to be confused with complexities. The first is that the redshift per distance correlation is in all directions. As gravitational redshift requires a geometric arrangement, this narrows the possibilities. The second difficulty is the mere fact that there is a correlation at all. As we will go into, it may appear as if the existence of the correlation proves that the redshift is not caused by gravity. Finding a model that uses gravitational redshift and successfully explains the redshift observations may prove to be impossible. The question becomes, is it possible for gravity to cause correlated redshift per distance for all distant galaxies in all directions? Gravity itself is mass dependent. This means that gravitational redshift depends on the mass of the redshifting object. This then means that if gravity is behind cosmological redshift, then it cannot be from each individual galaxy's effects, as each galaxy has a different mass and would thus produce a differing redshift per distance and thus not result in a correlation. This means that there is only one possible way gravitational redshift could cause correlated redshift per distance: if one single object is overwhelmingly influencing the light from all observed galaxies. Could this be?